Um, if you remember, back in section 1, that is chapter 8, section 1, we examined the concept of the sampling distribution of the sample means, and that is that we can get a close approximation of the population mean by collecting a set of samples, compute their means, and then add all of the sample means, divide by the number of samples to obtain what we call the mean of the sample mean that will ultimately describe the true population mean. Now, in this section, which is section 8.2, we are dealing with a different concept that is called the sampling distribution of the sample proportion or sample proportions. Now, if you remember, in a situation that deals with what we call a binomial experiment or a binomial process, which is associated with an event that can be either true or false, or success or failure, male to female, yes or no. These are what we call a situation that only deals with only two possible outcomes. And any situation that deals with only two possible outcomes is associated with what we call a binomial process. Now, the sampling distribution of the sample proportion is one example of that concept, which deals with a binomial property. And an example, let's say, what is the proportion of people in the United States will be voting for one particular political party in this new coming election. And another example would be, what is the proportion of American people who believe in world peace? So here, the question of interest is either we believe in world peace or we do not believe in world peace. So there are only two situations, there are only two possible outcomes, and that is governed by the sampling distribution of the sample proportion. Again, if you remember from section 8.1, that in order to obtain the true population mean, a description of the true population mean, we basically collect a set of samples, compute the means, and then compute the mean of those sample means. Now here in this particular section, we are dealing with the same situation yet with a different concept, and that is using the proportion. And if we, for example, let's say if we want to find out the proportion of American people who believe in world peace, we would collect, let's say, from a population, the entire US population, we would collect a number of samples. Let's say this is sample number 1, and this is sample number 2, sample number 3, and so on, all the way to maybe sample number 100. Okay, so here we collect 100 different samples from this population. Now, what we can do is we need to find the proportion, to estimate the proportion of, let's say, American people who believe in world peace. And the true proportion would be something like this, that the proportion is equal to the number of Americans who believe in world peace and that would divide by the entire population. So here, the number of Americans who believe in world peace is sometimes referred to as the number of observations. So So here we are basically computing the percentage of the proportion of people, the number of people who believe in world peace divided by the entire population. Now our goal then is, from this population, we will randomly pick 100 different samples, compute their proportions, and then find the mean of proportion that will ultimately describe the true population proportion. You see, the concept is quite similar to a discussion that we did in section 8.1. So here, for example, let me start a new sheet here, and still referring to this population from the Venn diagram, is that, for example, let's say if we collect our sample, let's say first sample number 1, we would get something like this. So let's say here sample 1, we would get, let's say our first observation is, let's say x is equal to 40 and our sample size is 50. Okay, now to compute the sample proportion from our first sample, we call it a point estimate by associating it with what we call a p-hat. So a p-hat is referred to as a point estimate, and since this is from sample 1, we will use a subscript of 1 to identify it. So here the point estimate is actually the number of observation divided by the sample size. So in this case, you have 40 divided by 50, and we get a proportion or a percentage, and in this case here, let's say it's 80%. Now suppose our sample 2, we get something like the number of observations, x, is actually equal to 35. And of course, we have the same sample size, so n is still 50. Now our point estimate for sample number 2 would be x over n again, which is 35 over 50. And that gives us 70%. Now you see here, our first sample predicts a 0.8. Our second sample obtained provided a 0.7. What about sample 3? So let's say sample 3, we have the number of observation 25 and n is still 50, and therefore the point estimate for sample 3 would be p-hat of 3, which is x over n, and that is 25 divided by 50, and that is giving us a let's say that's a 1/2, so it's a 0.5. So you see here we have different values of the point estimates, and we could probably go ahead and say that, yeah, the rest of these samples will have varying different values of point estimate. However, if we compute the mean value of all of these samples, and there are 100 samples, right here we have 100 samples. So if I just add all of these, so let's say, I have suppose, let's say, sample 100. So here we go all the way to sample 100, and sample 100, let's just say that p-hat of 100 is actually equal to, let's say, 58%. Now if we add all of these proportions, okay, and divide by the number of the samples, in other words, if we add all of these, I'm going to put the equal sign first, then we have p1 hat plus p2 hat plus p3 hat all the way to p100, right, and then divided by 100. You get the mean of the proportion, I mean to say the mean of the sample proportions, and this is what we call the mean of the sample proportion associated with mu of p-hat, and that will ultimately represent the true population proportion. So this is what we need to do to get samples from a population to get a close approximation that would be representative of the true population proportion, and we call this the mean of the sample proportions that will ultimately equal to the true population proportion. Now, you probably read this in my lecture note or in our textbook already. And then the second property associated with the distribution of the sample proportion is its standard deviation that has this expression. And I will write this down without proof. The proof is quite simple, but we don't have the time to do this. I like to make this video a little bit short here. Now here we have the product of P and Q, and if you remember, for a binomial property, for a binomial process or property, remember we are interested in only two possible outcomes. If we know the probability of success, okay, we can find the probability of failure, which is just a complement of the P. In other words, just 1 minus P. So this is what we mean by a probability of success multiplied by probability of failure divided by n. Or in other words, you can also write P times 1 minus P under the radical and then all over n. Okay, so that's another way of writing it. So these are the two properties associated with the sampling distribution of the sample proportion. Now, what is different than the sampling distribution of the sample mean that we looked at in section 8.1 is that the way we determine the condition or the property of the distribution, and that is that, you see, starting with chapter 7, we need to make sure that our distribution, the distribution of our data, has a normal distribution before we can convert it to the standard normal distribution so that we can use a z-table given in the back of the book. Now, if the data does not possess a normal distribution, then we cannot convert it to use a standard normal curve, because then we will have the, let's say the skewed left or skewed right distribution, and that would not be representative of the actual true population of the proportion. So the conditions for testing to make sure that the data has a binomial property, which in turn possesses a normal distribution, we have a number of conditions. Now the book presents us with the let me write this down first. Conditions. So the first condition is that the sample size must be no more than 5% of the entire population. So capital N here is the number, is the population size. Okay, the number of the entire subject within the population. Now this condition is applicable if the population size is known to us, and in many cases we do not know the population size. Okay, so this is kind of like what we call a conditional test condition, in a sense that if the population size is known, then this is the best way to check to make sure that the data whether it obeys the binomial property and that it has the normal distribution. So we'll call this condition number 1. Condition number 2 is that the product of the sample size, the probability of success, and probability of failure must be at least 10. If it fails, meaning that if the product of these three quantities is less than 10, then we know that it fails the test, and that is we cannot proceed to compute the properties of the sampling distribution of the sample proportion, because first of all it does not possess a normal distribution. The third test condition is something like this, that the product of N and P must be at least 5, and at the same time the product of N and Q must also be at least 5. Now these two conditions must at the same time satisfy, not only just one, but both of them must satisfy in order to confirm that the data has a normal distribution. Now you see, This is what we call a minimum testing. Sometimes this is what we call kind of a general passing condition. This is a strict passing condition. Sometimes if the data fails this condition, it may pass this one. So this is what we call a minimum passing. A fourth one that becomes very popular now is that the number of observations must be at least 5, and that the sample size minus the number of observations must also be at least 5. In a way, these two conditions kind of complement each other. If you can see here, they are related to each other simply because I'm going to just show us a little bit here, because you can see here that even though we don't use the p hat, but it stems from the idea of the p hat is that p hat is actually x over n. So if you take p hat times n, right, that gives us x at least 5. Now you see sometimes later on when we look at chapter 10, this will make much more sense, but right now it may be new to us to see the product of p hat and n. But later in the future, you see sometimes if the true population proportion is not given to us, we can use the point estimate to test the data. And this is what we mean by using the point estimate to test the data. Okay, well, more on this later on. But my point here is just trying to show you the relationship between these two right here, that they are intimately related. Just, you know, just a reverse product of these two quantities. Okay. So in many cases, in most of the problems that we deal with in this chapter, I will show us that if possible we can use this condition, and then if possible we can use condition. But I don't want you to lose sight of this, of the third condition as well, because this is the one that in fact we will be learning later on too, and that it will be used in the testing to conduct a project assignment that I will assign next week. Okay, and so these are the conditions that check and confirm that the data has a binomial property and that it has a normal distribution. If the test condition fails, if the data fails these one of these conditions, then we know that the data does not possess a normal distribution, and that therefore we cannot really do the statistical analysis of the data. And in other words, the data is simply just not usable. So the idea then is, given any data set in a sampling distribution of the sample proportion, you must apply one of these test conditions to make sure that the data satisfies the binomial test, or the fact that it has a normal distribution. If we find that it has a normal distribution, then we can proceed to describe the properties of the data. And if you remember, in order to compute the probability of any probability value associated with the proportion, what I mean is something like this. You know, let's say 0.5 or so, then we need to be able to test the data, and if the data satisfies a binomial property, then we can use the z-score to convert this. Okay, so essentially what we need to do then is the following lists the properties associated with the sampling distribution of the sample proportion, that we found that the mean of the sample proportion will ultimately be the true population proportion, and that the sampling distribution of the sample proportion standard deviation is actually sigma of p hat equals p times q over n, and that the translation of the general curve to the standard normal curve has this expression, which is z, which here, right here, is p hat minus mu of p hat divided by sigma of p hat. And sometimes we write it like this: p hat minus p, if p is given, and in many cases in this particular situation associated with this problem, yes, p will be given to us, and that will be divided by the square root of p times q over n. So here are the three properties associated with the sampling distribution of the sample proportion. Okay, and remember again that we can only compute this, z here if and only if the conditions are satisfied, you know, like n, the sample size here must be no more than 5% of the entire population, and that the product of p, q, and n should be at least 10. Okay, now one of these conditions, test conditions, must be used so that your data has this normal distribution. Okay, so if it possesses a normal distribution, then we can use the z equation here to convert it from the general distribution to the standard normal distribution. So you can see here the mean value in the middle, at the middle of the curve here, is p, and the mean value for the z is 0 in the middle. So this is what we call the standard normal curve, right? And that is given in the z table, and that's our goal here. We want to given our data for the sampling distribution of the sample proportion, we must test the data to make sure it has a normal distribution, and if so, then we are able to convert it to the standard normal curve so that we can use the standard z table to look up the value for any probability that we want to compute, something like this. So let's take a look at one example. Okay, and to do that, I'll let's see here, let me get rid of most of these first. Okay, let's take a look at one example from our textbook, I believe right here. Okay, let's take a look at number 9 here. So for problem 7 to 10, we need to describe the sampling distribution of the sample proportion and assume that the size of the population is 25,000 for each of these 4 problems. Let's take a look at number 9. Okay, so number 9. So number 9, we have the following. So we only need to describe the property of the sampling distribution of the sample proportion. In other words, we need to describe the p-hat distribution. That's basically, this is a quick way of describing what we need to do. Describe the p-hat distribution. That's what we want to describe. And how do we describe it? Well, we want to make sure that the data obtained to compute the p-hat, which is what we call the point estimate, has a normal property, and that is that it possesses a normal distribution, thereby obeying the binomial property. And what we need to do then is we need to test it first. Okay, so we call it test condition. And now you can see here the population size is given to us, Therefore, by default, we can apply the first test condition, and that is lowercase n must be at most 5% of the entire population. So here we have for number 9, here we have n equals 1000, yeah, and then we want to make sure that if it is less than or equal to 5% of the entire population, so here we're going to take 0.5 multiplied by 25,000, I mean. Okay, so here I'm going to do this on my calculator, and so we have 0.05 multiplied by 25,000, and that gives us 1250. So here we have, so here, wrong side on my notepad. So you have 1000 less than or equals to 1250. Is that true? Yes, it is true. So here the data that is given to us has a normal distribution. Now suppose this is good already, but let's test this by using the next test condition equation, and that is the product of n, p, and q. Is it possible? Yes, it is possible, because you see here p is given to us, right, which is 0.103. so p right here is 0.103. so if p is 0.103, then q is actually 1 minus 0.103, and that gives us basically a 0.897. And now here we have 1000 multiplied by 0.103 times 0.897. Is this at least 10? Well, let's do that. So here I have 1000 multiplied by 0.103 multiplied by 0.897, and that gives me 92. So here we have 92 greater than or equals to 10, which is also true. Okay, so we know now that the data satisfies the binomial test, and that it has the normal distribution. Now we are ready to describe the p-hat distribution right here, and the description of the p-hat basically involves the properties where mu of p-hat is actually equals to p, and in this case here it is 0.103, and that the standard deviation of the sampling distribution of the sample proportion is a square root of 0.103 times 0.897. Now remember how I obtained these from? Well, basically, if you remember from the previous worksheet, is that sigma of p-hat is actually equal to p times q over n. In this case here you have a 0.1303 and then 0.897 over 1000, and that's what I obtained right here. Okay, and if you take the square root of that product and the division, so let's do that quickly. So here I have a square root of 0.103 times a 0.897 divided by 1000. That gives me a 0.0096. So that is the description of the p-hat distribution, and that concludes this example. And for the next 2 videos, I will have a few other examples to help you work on the homework assignment. And to end this video lecture, I would like to give you the code. The video code is 0.103. That is the video code. So after you view this video, please remember to email me by this week on Thursday. Thank you.